Glycolysis. Okay, this is a topic that I frequently refer back to because it's so important to understand the flux through biochemical reactions and whether a reaction will act reversibly. So these are free energy considerations. We've talked about these before, so I'm not going to go into, I'm not going to spend a lot of time talking about this, but we have a couple different things here. We have, well, two different things really. We have the standard free energy change, and then we have the real deal, which is free energy under cellular conditions. We need the standard free energy change because that helps us develop an expression that relates the standard free energy change, which is this, to the real deal, as I mentioned, because what happens in the cell depends on the standard free energy change plus the term RT ln of Q. And that's the ratio of the products raised to their stoichiometric, the concentrations of the products raised to their stoichiometric coefficients over the concentrations of the reactants raised to their stoichiometric coefficients. So you can imagine if we have a lot of product, this term Q will get large. If Q gets large, the ln of Q also gets large, and we tend to make delta G more positive. That is not favorable to driving the reaction forward, right? In fact, that will suppress the reaction or push it in the opposite direction. On the other hand, if reactants are large, the concentrations of the reactants are large relative to the products, the opposite happens. Q gets small. If it becomes fractional, we start to get negative value for ln of Q, right? And then in turn, delta G starts becoming negative. Recall that a negative value of delta G, negative always means spontaneous, and positive always means non-spontaneous. So if we are high in reactants and low in products, we're going to drive the reaction to the product side. We're going to see that a number of reactions in glycolysis are reversible. Therefore, they can be changed. Their direction can be changed by changing values of the ratio of products to reactants. So these are physiological concentrations found in the organism, right? And those are changing all the time, depending on what's going on in the organism, what's going on in the body, energy needs, nutrient supplies, all this kind of thing, right? So these thermodynamic parameters can and do change all the time. So that's one thing we want to think about in relationship to glycolysis. The other thing is we're going to see in glycolysis and other metabolic reactions, things like the citric acid cycle and so forth, that there's a fair amount of redox. So, and in particular, we're going to see redox as driven by biological reactions in combination with coenzymes, things like NAD, FAD, FADH. There's a third one, FAD. So carbons are, what happens around the carbons is what dictates the oxidation state of the biological molecule. When I say biological molecule, that's not quite right. Let's say enzymatic metabolic intermediates, okay? So I think I may have referenced this before, but the bottom line is the more oxygen that you add to a carbon, the more heavily oxidized it is, meaning loss of electrons. And the more hydrogens you add to it, the more reduced it is. meaning a gain of electrons, right? But this is not the explicit loss or gain of electrons like we see in NaCl or something, right? This is not wholesale electron transfer. This is about electron sharing. So, so just to reiterate, as carbons gain oxygens in the form of, let's say, OH group or forming double bonds also count. The more double bonds we have, the more oxidized carbon is. And these always happen at the expense of hydrogen, right? So that means oxidation state going up, and then the reverse is true, more reduced as we have fewer oxygen and more hydrogens. We can actually assign oxidation numbers, but I'm not as concerned about that. I just want you to have the conceptual understanding that oxidation is largely defined in this context as the more electronegative atom, we can view it as owning those shared bonding electrons, because it's a covalent bond, right? The electrons are shared. But in the case of these metabolic intermediates and so forth, we're almost always dealing with carbon, hydrogen, and oxygen, right? These are organic biological molecules. So in the case where carbon is sharing with hydrogen, it is owning the electrons, right? In this most opposite and extreme case, where carbon is double bonded to two oxygens, oxygen is owning the electrons. And that's represented, carbon owning the electrons is represented by making these electrons red here. And oxygen owning the electrons is represented by them having blue electrons, right? So you can analyze all this. I mean, I don't need to go through this step by step, but you can see that each progression here, whether it's a double bonded situation or whether, it's the addition of an OH group or whatever it is, there is a progression here to increasing oxidation states. So that's just something you need to understand when we're looking at metabolic reactions. And the other thing to keep in mind is that oxidation never, ever happens without reduction. So when we're looking at metabolic reactions, if something is getting oxidized, the other thing is getting reduced. This here is NAD plus to NADH and in reverse. If this is just a portion actually of the NAD molecule, but it's where the action takes place. So if NAD gains the hydrogen, which we see it doing right here, it goes to the reduced form. So it goes from NAD plus to NADH. If the reverse happens, of course, this is an oxidation because it's losing that hydrogen. So, and gaining a double bond. So these are the coenzymes, as I mentioned. I feel like what did I say? NAD. I didn't say NADP. Anyway, does it matter? Not so much. These, what did I say? Someone tell me what I said. So these players, we're mostly, to be honest, we will look at NADP in some cases, but it's really going to be NAD and FAD that are the ones that we're looking at in terms of reversible oxidation states. So clearly they can accept electrons from a biological intermediate, or they can donate them to a biological intermediate depending on the situation. Okay, so now we can actually start talking about glycolysis. Who has studied glycolysis here at all? Even like, in what class?
Not in a class, but like self-studying for the MCAT.
Oh, okay.
Bio 101.
You do glycolysis in Bio 101?
The citric acid cycle glycolysis and the second photosynthesis.
Very interesting. Huh, you're taking that right now, right?
Last semester, so it's why I don't want to right
Oh, so you're more onto evolution and stuff like that?
now. Yeah, we're doing human anatomy.
Oh, interesting. How about you?
As well, I'm in college, learning nutrition and past chemistry courses kind of like, you know.
Touched on it a little.
And
Okay, anybody else? Bio 101? Do you remember every step and every enzyme and every like?
Wasn't that in depth.
This is going to be fairly in-depth, so be ready. Okay, so before we delve in, I want to talk a little bit about the fates of glucose because, you know, if you have studied glycolysis, you might think that glucose is meant to be broken down and that's all it ever does. It just is an energy source for us, and we subject it to glycolysis to generate pyruvate, and then maybe pyruvate goes on and goes through the citric acid cycle, or maybe pyruvate goes on and gets anaerobically oxidized. But there's a lot of other things that we don't necessarily think about. One that you may have encountered or thought about is that glucose, and we've even referenced this when we talked about carbohydrates, is that glucose can be polymerized to make glycogen, starch. It can make disaccharides like sucrose. So it can be a molecule for synthesis, not for catabolism, which is the breaking down of glucose. The other thing glucose can do, and we just really briefly touched on this, is it is a component of structural polymers, things like the cell wall and other structural polysaccharides. We're not really going to talk about that at all, you know, for the rest of this course. We will actually be talking, we won't really be talking about heavily anyway, the synthesis of glycogen, but we will be talking about the breakdown of glycogen to glucose, extracting energy from glycogen to extract the energy from it after it has been synthesized as a storage molecule. We will be looking also at something called the pentose phosphate pathway, which makes ribose 5-phosphate. That in itself can go on to help manufacture DNA molecules, for example, but it has a lot of other, the pentose phosphate pathways. Well, we're going to be looking at it. I don't need to get into it now. We will be looking at that, and that is a potential fate for glucose. But today, we're definitely just going to be talking about the oxidative breakdown of glucose to pyruvate. So glycolysis was the understanding of glycolysis is one of the great achievements of biochemistry. It was not an easy pathway to elucidate. You can imagine that 10 consecutive biological reactions involving 10 different enzymes is a huge thing to unravel. So there's that. The other kind of amazing things about glycolysis is that it was able to appear on Earth before oxygen was widely available, because it is essentially an anaerobic process. Anaerobic. It is universal. It is certainly not just us humans that do it. It is used by almost every living thing. It is a great process to just illustrate some of the fundamentals of the metabolic process and its regulation, which is hugely important. We need to know when to be performing the glycolysis reaction and when to slow it down, when to speed it up. And there is a very intricate dance that is put in play to regulate glycolysis. There are certain things you're going to want to memorize: the names of the compounds, the natures of the reactions, and the key enzymes. This up here is just the overall reaction. we want to start thinking right away about what we generate, not just in terms of the pyruvate, but importantly, we get NADH out of this process and ATP. These are the net gains. We get 2 for every molecule of glucose. We get a net gain of 2 ATP, of 2 NADH, and we get our 2 pyruvate. We have definitely not extracted all the energy we can from glucose at this point. Pyruvate has a lot more to give. ATP is clearly an energy currency for the cell, so that's a plus. And NADH as an electron carrier is also extremely important. Eventually, we're going to look at oxidative phosphorylation, and NADH is an electron carrier that donates electrons to the oxidative phosphorylation process. So as mentioned, glycolysis is a 10-step pathway. As I already mentioned, catabolism or something getting catabolized is just a term for breaking down a molecule rather than anabolism, which is synthesis or building up of a molecule. We have a series of enzyme catalyzed reactions. And I have, throughout this lecture, I'm going to show you the process in different ways. I've selected various images from the internet or the textbook, and each one of them is a little bit different. I would say the one that we're looking at here is fairly one of the more simple ones, but that can be good, right? This just highlights kind of the main events. And it also, one of the things I liked about this figure is we're going to see how important phosphorylation is to this process. And you might notice that every single intermediate in this reaction is phosphorylated. So that really highlights the where and the, in a very simple way, but it really highlights that point, let's say. This gives you all the intermediates and all the enzyme names. So it is an oxidative process, although interestingly enough, only one reaction is oxidative, even though we call it an oxidative process. We'll point that out. I'll point that out when we get to it. As pointed out already, some of the free energy of this catabolic process is preserved in ATP and NADH, and pyruvate can go on for further action. So there are 2 phases. There is the preparatory phase, which is up to here, and then there's the payoff phase. So we're going to break this down into 2 segments. In terms of free energy, the transformation of glucose to pyruvate is indeed exergonic. But we also have some energy costs. So the exergonic is, if we look at this reaction right here, we see glucose and NADP being converted to pyruvate and NADH. But we also know we have a net yield of ATP in this reaction. And it is in fact costly to add inorganic phosphate to ADP, which we will be doing, and that costs energy. So the negative free energy here is our bonus prize. The positive free energy here is a cost. So the good news is we can consider these essentially to be coupled, and we can add these 2 free energies together and find that the overall process still has a negative free energy, which is good. We want that. Just hide these. Another thing to notice, we'll be getting into that, but we actually consume some ATP in this reaction. But there is still a net yield of plus So we consume 2 ATP in the preparatory phase, but we make 4 ATP in the payoff phase. So we get a net yield of 2 ATP. This will all be clearer. We're taking a 6-carbon molecule and we're breaking it in half in the preparatory phase to get 2 3-carbon molecules. And then each one does exactly the same thing to generate, in the end, pyruvate. But you can kind of see already how this would be the preparatory phase, right, where we're consuming things, and how this would be the payoff phase here, where we're making these NADH and ATP. Okay, so I'm giving you the framework here, and we're going to go reaction by reaction. I want to make a point of what pyruvate can do at the end, which I've already talked about a little bit. I've said it can go on to the citric acid cycle and oxidative phosphorylation, which will definitely get the most bang for our buck in terms of what we can extract from the glucose molecule. But we don't always have aerobic conditions, right? We're running a marathon or we're doing heavily exercising or something. We may be reduced to more anaerobic conditions, in which case pyruvate in the human body can be reduced to lactate. And some bacteria are in the business, or yeast, microorganisms, let's say, are in the business of taking pyruvate and reducing it to ethanol. Lucky for us. Some of us. So pyruvate can also, there's actually another possibility, which it can provide the carbon skeleton for things like alanine synthesis or fatty acid synthesis. So this picture over here illustrates the potential different fates of pyruvate we have in microorganisms, as mentioned. If anyone here drinks beer, one of the things that goes on when you brew beer is you take advantage of yeast to produce ethanol, and lactate, as noted, can happen under anaerobic conditions in our bodies, and in other situations, there are lactic bacteria also, so bacteria can make lactate. And then, of course, this represents the citric acid cycle, the ultimate conversion of pyruvate to CO2 and H2O, and the generation of a lot of ATP. Okay, so we saw previously in that first figure showing the 10 steps of glycolysis and highlighting the phosphorylation. We saw how important phosphorylated intermediates, or how ubiquitous, how ever present these phosphorylation states are to the glycolysis reaction pathway. So all 9 intermediates are in fact phosphorylated, as we saw. What does this do for us? Well, one of the very first things it can do is it can prevent glycolytic intermediates from leaving the cell. We have these glucose transporters, right? So once we get them in the cell, we may want them to stay there. Glucose 6-phosphate is a prime example of that. It's the very first step of glycolysis. We phosphorylate glucose and it can no longer leave the cell unless it gets dephosphorylated, but it most likely won't. So so that's one. Another huge point is that it helps conserve the energy found in our biological intermediate. Whenever we add a phosphate or to a metabolic intermediate, that is a high energy bond, right? So it actually makes our compound more unstable. And that can be good if we want that compound to react, right? We can't get the progress through the various reactions that we need without phosphorylation, because the chemistry just wouldn't happen. We need it. And then interestingly, it can also have a catalytic effect. It can lower the activation energy, and it can increase the specificity of the particular enzymatic reaction at hand. So these are some of the things phosphorylation can do and why it's important. And I want you to, as you're studying glycolysis, I really want you to think about certain things to help you. I mean, to help you rather than just sitting around memorizing, you know, hexokinase enzyme 1, the hexokinase isomerase reaction 2, you know, so phosphofructokinase is the enzyme for reaction 3. I mean, you can sit around and you can memorize these things, and there's going to be some of that. But I also think if you follow what my recommendations here, it will be more interesting. It will be easier to remember, and it will all hang together conceptually a lot better. So one thing to do is to follow the chemical logic of the steps. We're going to be looking at some of the mechanisms, but more than that, like we just talked about phosphorylation as an example, or why is it important to split, you know, the fructose 1,6-bisphosphate into 2,3 carbon molecules, you know, that kind of thing, the flow of the reactions. The next thing is a lot of the enzyme names tell a story. They're describing the kind of reaction that they're catalyzing. So that can be helpful. Keeping your eye on the free energy of the reactions. Some are essentially irreversible. They tend to be points of regulation. Some things are highly reversible, so that's important. So these two things are basically part and parcel of one another. Redox, as I have pointed out, is important. And again, points of regulation, which are, again, tend to be the exergonic steps. And just a hint, all tend to involve the formation of ATP. Except the first one. So I should modify that. Several of them involve the formation of ATP. Okay, so this is an overall look at the preparatory phase. And this has to do with what? Well, we're starting with a hexose carbon. Guess what? Better known as glucose. And we have what is known as a series of priming reactions. We are priming our molecule with phosphate, right? And we're also readying our glucose molecule for cleavage into 2,3 carbon molecules. I would say that is the major big picture of what's going on here. Phosphorylation, developing this symmetrical molecule, and then cleaving it. The end game is that we're taking a hexose carbon and we're converting it to 2-glyceraldehyde 3-phosphates. So we start here with this ring molecule, right? Incidentally, any ring molecule is going to have to be linearized before a reaction can go forward. And through a series of steps, I'm going to be going through these one by one, so there's no point in talking about all of them right now. We're going to end up with 2 G3Ps, glyceraldehyde 3-phosphate. Also notice, I've said this before, but it can't hurt to mention it again, ATP is getting consumed in this part of the reaction too, in the phosphorylation process. Okay, so the first step is catalyzed by an enzyme called hexokinase. And remember I said the enzyme names tend to tell a story? Well, what does this sound like? This sounds like something that is phosphorylating a 6-carbon sugar, namely glucose, right? So it's going to phosphorylate glucose at carbon 6 to yield glucose 6-phosphate. In my heavier design moments when I'm doing PowerPoint slides, I try to color code things to help them make sense for you. So I'm putting the enzymes in green and the product in purple. What are a few things that we want to say about this reaction? Well, 1 ATP is consumed, right? Hexokinase, like a number of enzymes in the glycolytic pathway, requires magnesium 2+ as a component of the enzymatic reaction. So, and we talked about that way back when, right? When we were first studying enzymes. Why magnesium 2+? It helps stabilize the negative charges on ATP. Another thing that's interesting about hexokinase is it provides a very good example of induced fit, which we talked about previously. It's able to wrap itself around the substrate in such a way that it facilitates the transition state. And then, as mentioned previously, not only does phosphorylation activate glucose for further reactions, but it also makes sure that this molecule stays inside the cell. So we can consider this to be a high energy bond, and we're also adding a group that prevents it from going out through a glucose transporter that it came in. It is an exergonic reaction, negative 16.7 kilojoules per mole, so it tends to go only in the forward direction. Step 2, we have to take glucose 6-phosphate and convert it to fructose 6-phosphate. Good thing you know these carbohydrates so well at this point, right? These are like molecules that you definitely know. So this is a reversible reaction. Again, phosphohexose isomerase. We're just rearranging the structure of this molecule, taking it from glucose and turning it into fructose. Still a 6-carbon sugar, right? Again, requiring magnesium 2+. And note that this is readily reversible. So that is reflected by a delta G value that is, the standard delta G is very close to that tipping point, right? It could go negative, it could go positive, depending, this being our product and this being our reactant, the relative concentrations are going to dictate whether this is going in the forward direction or is it going backwards.
So it's not always on the endogenous.
Exergonic? Absolutely not. There are only certain steps. Well, this is endergonic as written right here, but no, it can, that's the whole point of the delta G equals delta G plus RT ln of Q, is that this Q term can take this 1.7 value, which is just barely positive, just barely endergonic, right? And it can become negative or it can become positive. So, and one thing that we're going to study is we're also going to study gluconeogenesis. Now, gluconeogenesis is not the exact reverse of glycolysis, but some reactions are shared in common, right? Gluconeogenesis is the formation of glucose from pyruvate. So some of these things just need to be readily reversible. We'll get to that, but I don't want you to think of glycolysis as a one-way street necessarily. There is potential for reversing things, except for the exergonic steps. So gluconeogenesis has to solve the problem of the irreversible steps. It has to find a detour, shall we say. Okay, so what chemical logic, what has this done for us? Well, eventually, we've now got fructose phosphorylated at C6, but we actually want to phosphorylate it here as well. We want to add a phosphoryl group here. And then you can see it's going to be nicely symmetrical and ready to be cleaved. So this isomerization reaction prepares us for the dual phosphorylation. We've already got the phosphorylation of carbon 6, but in the next step, we're going to get phosphorylation at carbon 1. But before we do that, we're actually going to look at the mechanism of this reaction. So, and why are we looking at this one in particular? Why didn't we look at the first one? Well, you know, the ones that I've chosen to actually illustrate the mechanism show something interesting about the chemistry, about acid-base catalysis. In particular, this one highlights the acid-base catalysis aspect. So what goes on here? Well, we have our glucose 6-phosphate, right? And we want to isomerize it. So notice a few things. This is not identified here as glutamate, but it is in fact the active site glutamate that is serving as a general base. And what does it do? It abstracts a proton from our linearized glucose molecule. And as it does, we get a double bond formed here, and this becomes a negatively charged oxygen, right? So this picks up, of course, this picks up a hydrogen pretty quickly. And what's interesting here is that no sooner has this base picked up this proton than now it's ready to just break this. This double bond is now going to abstract the proton here, right? So it's going to turn around and act as an acid now, having just abstracted a proton. But this is going to facilitate this isomerization, right? Because now this OH group here, when this proton is abstracted, we're going to get the double bond and we're going to form the keto. Whereas we started up here with the aldehyde, right? So it's just base catalysis followed by acid catalysis gives us the keto sugar that is fructose, and then it goes back to the ring form, and we have our fructose 6-phosphate molecule. Transition from aldo to keto sugar. So what is the name of the enzyme? Phosphohexose isomerase. It's taking a phosphohexose and it's isomerizing it. Okay, so as noted, fructose 6-phosphate is now our reactant, and it sets us up to generate fructose 1,6-bisphosphate. This is a particularly important regulatory step. So this is an enzyme you definitely want to get cuddly with. It is called phosphofructokinase 1. What do kinases do? Generally, we think of kinases as phosphorylating things, right? So indeed, that's what happens here. We have ATP as a substrate for our reaction, as well as fructose 6-phosphate. And again, notice pretty much whenever we have ATP, we're going to have the magnesium ion. So ATP gives up its phosphate to go here, and we generate ADP as a product, as well as the fructose 1,6-bisphosphate. This is, again, We saw hexokinase as having a fairly large negative free energy. This is also an exergonic and essentially irreversible reaction. The other very interesting point here is this is the first committed step in the glycolytic pathway. Now, you might think that anything exergonic is committed, right? But that's not true. The reason that's not true is glucose 6-phosphate, which is the product of the hexokinase reaction, can leave the glycolytic pathway and go off and do other things. It can be siphoned off from this, what we think of as this very linear pathway. Things can get siphoned off along the way. Once we have fructose 1,6-bisphosphate, it has no other fate than to go on and continue through glycolysis. And that's what we mean by committed, not exergonic, not irreversible, but no other siphoning or other direction to go to. You can't run away from home at this point. You got to go through glycolysis. Okay, so now this is ready. As you can see, we have the possibility for a split here, right? And to get two, if not identical, at least two similar molecules. So before we get on to that, this is a very important regulatory step for glycolysis. Not only is a committed step, but it is highly regulated. One distinction I want to make right now is I kind of made a deal about the reversibility of reactions and that they can go forward or backwards. And that's going to be controlled by prevailing concentrations of reactants and products, depending on what's happening in the cell. But when we actually say regulation, we mean like allosteric regulation, for example, right? So, or regulation by, in fact, phosphorylation. We're going to see we have covalent regulation, we have allosteric mechanisms. So when I say regulated, that's what I'm talking about. I'm not talking about the ebb and flow. I'm talking about actual regulatory mechanisms. So we're going to look at the allosteric regulation of PFK in a lot more detail when we really go full on with the regulation of glycolysis. But I think it's already good to point out right now that it's an important regulatory step. There's something called the reciprocal regulation of glycolysis and gluconeogenesis that is involved here. For now, we're just going to say PFK1 activity increases when cellular conditions indicate the need for ATP. And that should make perfect sense because we need ATP when our energy stores are low, when the ATP supply is depleted, and we have an accumulation of ADP and AMP. Another molecule enters the scene, which is not actually part of the glycolytic pathway. And this can get confusing because it has a very similar name to one of our glycolytic intermediates. It is something called fructose 2,6-bisphosphate. What does that sound a lot like? We just looked at fructose 1,6-bisphosphate, right? In fact, this is the molecule that's getting cleaved in this reaction. But this is not the allosteric modulator that is fructose 2,6-bisphosphate. So fructose 2,6-bisphosphate, if it accumulates, is a very potent allosteric activator of the PFK1 enzyme and therefore of glycolysis. And another molecule, ribulose 5-phosphate, can also indirectly activate glycolysis or an NPFK1. Stay tuned. Okay, so now we want to look at the cleavage of fructose 1,6-bisphosphate. And in organic chemistry, even if it was many moons ago, you probably studied something called the aldol condensation, which is the formation of carbon-carbon bonds. Ring any bells? Yes, okay. In this case, this is a reversible reaction. So this could be the cleavage of a carbon. I mean, this could be the formation of a carbon-carbon bond, but actually in terms of glycolysis, which is a breakdown, we're going to be considering this in terms of a reverse aldol condensation, or in other words, breaking a carbon-carbon bond, not forming one. Now, this is reversible, so it could be the formation, but as I say, right now, we're going to be looking at it in terms of breakage. So this should say bisphosphate, by the way. So this is catalyzed by a reaction called aldolase. How do we remember that? Well, aldol condensation forms carbon-carbon bonds, and in this case, reverse aldol, break carbon-carbon bond. What are we going to get out of this? We're going to get 2 3-carbon molecules. We're going to get something called DHAP, or dihydroxyacetone phosphate, acetone, right? And glyceraldehyde, 3-phosphate, aldehyde. Very similar looking molecules, except the position of that carbonyl group has changed, right? Carbonyl. I don't know. I have weird pronunciations. So these are our products, G3P and DHAP. You're welcome to use the abbreviations because these get very wordy. Throughout, you can use, fructose 1,6-bisphosphate is F16BP, for example. So feel free to use those and get to know them. It's useful to get to know them. So this is readily reversible by virtue of reactant or product concentrations. And we're also going to see that DHAP does not make the cut when we go to the payoff phase. It's actually going to be, all of it is going to be isomerized to G3P. And that's the 3-carbon molecule that's going to be funneled to the payoff phase of the glycolysis reaction. So we're going to take a look at this mechanism because it's an excellent example of covalent catalysis by lysine, and generally an interesting reaction. So lysine is our nucleophile here. And as we've seen previously, we saw it with serine in the chymotrypsin reaction. This is, lysine has the R group that's going to perform a nucleophilic attack on our fructose 1,6-bisphosphate after it has been linearized in the catalytic site, in the catalytic active site. So it's going to do that, and we're going to see again that we have important roles for acidic and basic residues throughout this mechanism. Those are not necessarily going to be identified, but we can note their presence, right? We have molecules or amino acid residues that are giving up protons and ones that are performing as bases and accepting protons or abstracting protons. So that's what immediately happens here, right? One of these basic residues, as soon as the R group of lysine has performed this nucleophilic attack and formed a tetrahedral intermediate, this base is going to come in and take this proton away. And this is going to lead to the formation of a double bond right here. So what does this give us? This gives us something called a protonated shift base. Apparently, this is a term biochemists like to use. And here it is, a protonated shift base is what you see right here. It is recognizable by this double bond between the glycolytic intermediate and the nitrogen of the lysine R group. And it sets us up. What this protonated shift base does is it sets us up to actually perform this carbon bond cleavage between carbons 3 and carbon 4 of our 6 carbon molecule, which is exactly where we want it, right? So what happens? Well, this double bond, these electrons go back to nitrogen, and then the breakage happens right here. So we get, while this is all happening, this second basic residue abstracts this proton. We form a double bond here between the carbon and the oxygen, and we actually release glyceraldehyde 3-phosphate at this point, right? So you can, just take a moment to look at all the chemistry that's going on right here. But what does this mean? We're still, this double bond goes away, but we formed, now we have a single bond here between lysine and one of the carbons. So we still have the other half. G3P has been released, but we still have the other half of our, what was previously fructose 1,6-bisphosphate. We still have the other half attached, covalently attached in the active site of our enzyme. So now what? Well, guess what? We get reformation of the protonated shift base, right? The electron pair from this nitrogen molecule goes back to form the double bond. And in the meantime, this acidic molecule here goes to attach itself to this carbon, right? So then we have just the reformation of a protonated shift base. It's not exactly the same molecule as we had up here, but it looks similar, right? So finally, this sets us up for the release of DHAP. And basically, it's just a hydrolysis reaction. Water comes in, and we get water added where this bond gets broken, and we get an OH group added here, right? And we get rid of this bond. So that gives us our second molecule, DHAP. So we cleaved between carbon 3 and 4, and we have our DHAP, and we have our G3P. Similar looking molecules, but not identical. As noted, now we want to go forward, and we want to turn all our DHAP into G3P. This, again, I can't emphasize enough, this really sounds like what it's doing. It's taking a triose phosphate and it's isomerizing it. Triose phosphate isomerase takes all our DHAP and converts it to G3P. This is a reversible reaction, but if we're going in the forward direction, we're going to get all G3P. We're going to head to the payoff phase. And this is the final step of the preparatory phase of glycolysis. Readily reversible, why? 7.5 kilojoules per mole is not insurmountable. So it can go depending. Okay, I'm gonna look at this slide. I'm gonna look at this slide. You can look at it too. No, I'm going to talk about this slide, and then we're going to take a break because this is a lot of information to take in, and it's a lot to communicate. So one thing that's interesting to take note of is after this final step of the preparatory phase, the atoms from carbons 1, 2, and 3 of the starting glucose cannot be distinguished from carbons 6, 5, and 4, 4, 5, and 6, if you prefer. And that's because of this isomerization reaction. I mean, we can, when we know for DHAP that it's carbons 1, 2, and 3, right? And we know for glyceraldehyde 3-phosphate that it's carbons 4, 5, and 6. But when this isomerizes, right, it becomes this. So we don't really know what came from what in the end, right? And why do I bring this up? Well, you can imagine, let's say you're doing some kind of experiment and you're using some kind of isotopically labeled carbon to try to figure out what's going on in your reaction, right? If you can stop the reaction here and you can isolate these two molecules, you could potentially identify where your carbons are. But after the isomerization reaction, it's anybody's guess as to what's what. So let's take a break. I'm going to call it 2:25. Let's take 15 minutes, 2:35. No. Help me out here. 2:40, right? Has anyone taken genetics here?
Taking or taking?
Either.
Yeah.
Do you have the syllabus?
Do you want to, well, I didn't take it at this school specifically, but do you want any genetics?
No, no, I meant here.
Oh, sorry.
Where'd you take it?
ECC,
Where?
Morris Community College.
Okay. What did you study like transcription, translation, DNA repair? That's what I thought. I mean, you do Mendelian stuff as
Oh, yeah.
well, right? Plenty of that, yeah. So no one's taken genetics here besides you, Emanuela.
I've taken it
Oh, yeah, where'd you take it?
at Wheaton College, Massachusetts.
Oh, okay, yeah. So, same thing?
Yeah.
I'm curious about like, I'm part of this post-bac pre-medical program and like, they're taking both the semesters of bio, they're taking biochem with me, ultimately, they've taken genetics. And I'm also going to teach them cell and molecular biology. And I'm just, there's so much redundancy, you know? I'm like, and I'm trying to convince them not to like just do the standard syllabus for cell and molecular, because I'm not going to sit around and talk about glycolysis again and transcription and translate, you know, like that would be insane. They're going to hate it. So what I want to do is like talk about some about immunology, some about cancer, some about like emerging gene technology, you know, genetic engineering technologies, make it a little more topical rather than just like survey.
Yeah. It is redundant.
Yeah. I mean, does this course feel redundant to things you've done? No, okay.
Chapter 7 and 8 maybe, but that was it.
7 and 8 because of membranes and things?
No.
Wait, no, 7 and 8 were, what, 7,
The
I
DNA stuff and then like the Fisher protection, the Hawthorne, like I feel like that was like, you know, we don't know DNA stuff. Like,
yeah, that's what I think. That's why I kept
Yeah.
that so very short,
And
you
then,
know?
like, the Fisher projections and Hawthorne, that's just like orgo. Besides that, everything is like, new.
Okay.
I'm so sorry.
What? That's all right. You just have to share.
Should we know the covalent catalysis of lysine?
One thing I was thinking about is where I show the mechanisms. I think one of your study goals should be, no, do you have to write this whole mechanism? No, but for the mechanisms that I've shown, we have a covalent catalysis by lysine and the formation of a Schiff base. So those are kind of the highlights of that reaction. As a means to doing this reverse aldol concentration. So you should be able to sort of line all that up. But, in terms of what are the important things of the other mechanisms that I showed? In the isomerase reaction, it was, the thing that I was trying to emphasize was the importance of acid-base catalysis with an active site glutamate, and how that facilitates the transition from an aldo to a keto sugar. So those are just really the highlights of these reactions. And then I forget what I've talked about at this point. And in this one, it's the formation. We haven't talked about this one yet, but in this one, it will be a certain other thing that you should be focusing on. But draw the whole mechanism? No, absolutely. That would be too much. So you're studying for the MCATs right now?
Mhm. Yeah.
Are you taking them soon?
I was, but I'm choosing to apply next cycle instead.
Okay. Have you graduated from Wheaton yet?
Mhm.
Okay. So you're doing, and you live here, presumably, so,
Yeah.
okay. Do you have other courses that you're gonna take, or is this it?
I think this is it. Yeah. I audited biochem back in undergrad. Don't remember too much of it. And plus, like when you audit it, it's the same pressure.
The stakes are not, are not as high. Okay, I guess it's that time. Time for a payoff. Okay, so just taking a big picture view at the payoff phase. So far, we've used ATP, right? Now we're going to make ATP and NADH. So we're going to look at the chemical process behind that. The other thing to keep in mind, and this can be a little confusing, is even though we're treating each one of these reactions individually, everything is ×2, right? Because for every molecule of glucose, we're going forward with 2 molecules of G3P. So that means if we look at a reaction that appears to just be giving us 1 ATP, it's really in stereo, right? Because we'll be talking about the conversion of 1 molecule of G3P. Anyway, you get the idea, I think. So what are we going to get overall? We're going to get 4 ATP and 2 NADH per 2 G3P. And we're going to be getting 2 pyruvate per 2 G3P. So we're going to have our oxidative reaction. We're going to have phosphorylations, but this time the phosphorylations are losing the phosphates on our metabolic intermediates and giving them to ATP, right? So that's one consideration. So the redox is going to happen here. Then the generation of ATP is going to happen here. Note that both of these ATP forming reactions, there's a first one and a second one, are going to involve something called substrate level phosphorylation. And I'm going to explain what that is. It's very much what it sounds like. Always good to keep in mind the overall equation. I'm not going to read it to you, but it's always there for your reference. Okay, so the first step of the payoff phase, i.e. step 6, is the conversion of G3P to of G3P glyceraldehyde 3-phosphate to 1,3-bis phosphoglycerate. Now, this is a phosphorylation reaction, but note that this is a very different phosphorylation reaction. We are not using ATP. We're using inorganic phosphate. So that's one thing to take note of. The enzyme itself is called G3P or glyceraldehyde 3-phosphate dehydrogenase. The dehydrogenase is a big clue that we're involved in a redox reaction. We are oxidizing glyceraldehyde 3-phosphate and we are reducing NAD+. Okay, this is a bit unusual to be adding an inorganic phosphate directly to our substrate. That's just something to take note of. Why? Because it's not an easy reaction. It's not easy to add inorganic phosphates to biological molecules. How is this going to go forward? Well, we're going to oxidize the aldehyde group of G3P to a carboxylic acid that ultimately forms a phosphate anhydride. This acyl phosphate is an important intermediate because it conserves free energy. In fact, this acyl phosphate bond that we have here has a very large and negative hydrolysis. The free energy of that hydrolysis is negative 49.3 kilojoules per mole, which is extremely large. But that's not the overall free energy of this reaction. This is actually a reversible reaction at 6.3 kilojoules per mole. We're going to take, this is the last mechanism we're going to look at. And it has its own distinctive features. So again, to answer your question, that's what to focus on, the distinctive features of the mechanisms that I'm showing to you. So in this instance, this is the first time we're going to see cysteine actually acting as a nucleophile. And the environment of this active site, cysteine, actually reduces its pK. It goes all the way down to 5.5 instead of 8. And that puts it in its most, part of the reason this active site environment allows for reduced pKa is the binding of NAD+. So this is, of course, a more reactive form. It has this negative charge. It's in its thiolate form, and it is going to be very reactive towards the carbonyl group on G3P. So what happens here? Well, we've seen this over and over again, right? Nucleophilic attack. The electrons from the double bond go to the oxygen molecule. It assumes a temporary negative charge that we see here. And then it quickly reforms the carbonyl group and gives up its hydrogen, in this case, to the NAD+. So this is what? This is a thioester intermediate that we have on our hands here. This is in the way, sorry. So this thioester, this is quite an important structure in terms of this mechanism working, because this is, again, a not very stable situation. And because it's not very stable, it's going to allow the addition of this inorganic phosphate to the molecule. So here, several things happen. NAD+ and the inorganic phosphate both come in. The NAD+ is reduced to NADH, and this endergonic addition of the phosphate group is coupled to the thioester breakage here, right? So at this point, the cysteine is released. The phosphate gets added in. We maintain our carbonyl here. And we now have the molecule we intended to get, the 1,3-bis-phosphoglycerate. Okay, so at this point, our enzyme is regenerated. It's ready for another round, and we're good. So what's important about this? I would say the formation of the thioester intermediate with the cysteine residue allowing the endergonic addition of the phosphate group to our molecule.
Is that coupling what makes it favorable to take place, or?
This is what allows it to go forward. The free energy is actually slightly positive, but again, you know, like close enough that, and it is a reversible reaction, but yes. Okay, so now what has to happen? we have 1,3-bisphosphoglycerate, and now the fun begins because we get to start forming ATP. We just formed NADH in the last step, right? And in fact, we did it ×2, right? We got 2 NADH here. In this case, we're now going to start forming ATP. And one thing I want to point out is this is a kinase enzyme, phosphoglycerate kinase, but normally we associate kinases with adding phosphates to biological substrates, right? So we already saw hexokinase, phosphorylating glucose, and we saw PFK1, phosphorylating fructose 6-phosphate to make fructose 1,6-bisphosphate. So those were 2 kinase react. Both of those were kinases, but we were actually adding the phosphate to the hydrocarbon molecule, hydrocarbon oxygen molecule. This time it's a kinase, but it's not as we normally think of it. We're actually taking the phosphate group from our molecule here and we're adding it to our ATP to get ATP and reducing the phosphorylation state of our molecule by 1 to 3-phosphoglycerate. So this is in fact substrate level phosphorylation, and all that means is our substrate molecule, which is our 1,3-bisphosphoglycerate, is donating its phosphate group to ADP. So again, this happens in stereo. So we're going to get 2 ATP. Notice the large negative free energy here. So this is a pretty exergonic, not reversible reaction. Alrighty then. I'm just kind of studying these, meditating on these dual arrows. Essentially irreversible. Okay. What's happened so far? I think it's always good. You know, it's so hard to keep the big picture in your head while like getting sort of sucked into all these details, right? So we went down a phosphorylation step, having just added, what's the narrative here? Having just added a phosphate molecule to G3P, what we giveth, we now taketh away in the next step, and we use it to phosphorylate. So isn't that interesting? You put on an inorganic phosphate and then you immediately use it to phosphorylate an ADP molecule. Okay, so that's our narrative. And now we're going to have kind of, I wouldn't exactly call it a pause, but we're going to take our 3-phosphoglycerate and we're going to have another kind of movement here. It's not exactly, I don't know, would you call this an isomerization? I guess in a way it is, but we're moving the phosphate group this time, right? So it's phosphoglycerate mutase now. This is a reversible reaction, and we're just moving the phosphoryl group actually from carbon 3 to carbon 2. So phosphoglycerate mutase. I don't expect you to memorize where, you know, these positively charged ions are involved all the time, but notice they are like quite frequent players. Reversible delta G. Now we have 2-phosphoglycerate. We've only made one set of ATP, so this character is going to have to be given up eventually. We know by the time we get to pyruvate, we don't have any more phosphates on our molecule anymore, right? Okay, so, and yet we're going to have, we still have one more step to go here before we give up this phosphate. So we're going to now take the 2-phosphoglycerate and we're going to form a molecule called PEP, or phosphoenol pyruvate. This is again a reversible reaction, and we're simply removing a molecule of water here. The molecule of water is going to be giving us this double bond between the, we're losing these here. We're forming the double bond between these two carbons. We're not going into the mechanism here, but we do have a magnesium ion stabled enolic intermediate. Okay, now we're going to have our second substrate level phosphorylation, because we're going to take PEP and we're going to use it to, again, perform a substrate level phosphorylation on ADP. We're going to get this again times 2, and we have our pyruvate molecule. And that is it, step 10, right? I think I got to plug in my computer. So let's think about what we did. We had, this is good for me as well as you. We took G3P, we added a inorganic phosphate to it. What did that form? Look it up. G3P becomes 1,3-bisphosphoglycerate, right? 1,3-BPG, am I correct? Okay. 1,3-BPG, what do? We move the phosphate, right? From carbon 3 to carbon 2. That is called, somebody help me out because I'm not sure. I feel like I skipped a step. Yes, okay, I skipped a step. We did get 1,3-bisphosphoglycerate, and that was the first substrate level phosphorylation. So that gave us 3-phosphoglycerate, right? And that goes to 2-phosphoglycerate, courtesy of phosphoglycerate mutase. And then we have the enolase reaction, which takes 2-phosphoglycerate to phosphoenol pyruvate, or PEP. And then PEP, courtesy of pyruvate kinase, because even though we're removing the phosphoryl group from PEP, it's still a kinase reaction, and we're generating pyruvate while forming ATP. Are you as exhausted as I am? This guy never wears out over here. It is interesting, but it's a lot of talking. Trust me, you come up here. I'm picking on him again. I like to pick on this guy. Large negative free energy, right? We ain't going back here, at least not the same direction we came in. This is definitely one of those reactions, among others, of the exergonic reactions here, where we're not, when we talk about gluconeogenesis, we're going to have to do an end run around this reaction for any number of reasons. One, we don't want gluconeogenesis to be the exact reverse of glycolysis, because that would just be a futile kind of back and forth, right? We want, and so in order to reciprocally regulate these things, not only do you have to find a way to bypass the highly exergonic reactions, but you want points of regulation where you can inspire one to go while the other is stopping, right? You just don't want a symmetrical back and forth. Okay, one note about this reaction is pyruvate can be formed in its enol form. It will spontaneously tautomerize to the keto form, which is the pyruvate that is going to go forth and do its thing either anaerobically or aerobically. Okay. So here is the whole shebang. Do I have anything to say here? I'm not sure. But I mentioned before, right? I mentioned before that certain different things, like I showed you that pretty simple schematic of all the 10 steps of glycolysis in that first. I mean, I think this also highlights the nature of the phosphorylation, but it doesn't show it in quite that same way where, you know, you're really highlighting in a more simplified way. This certainly highlights the consumption of ATP in the preparatory phase. So we have, you know, and this kind of breaks it in a different way. This gives us sort of a top and bottom, preparatory and payoff. This highlights the carbon, you know, the carbons. We have green carbons and blue carbons here. So we see where they split off in the formation of DHAP and G3P. But as we noted, once DHAP isomerizes to G3P, we kind of really don't know the fate of the carbons at that point. Certainly have all the enzyme names here. We see the addition in the payoff phase of the inorganic phosphate, and that we have a redox reaction going on here, and that we have the generation of NADH, et cetera, et cetera, et cetera. Chemical logic. So I don't think I really have the energy to go through all this with you. So I'm going to let you study this one on your own in terms of thinking about, you know, we talked about some of these things already, though. I'll point out a few things. Phosphorylation here ensures that the pathway intermediates remain in the cell, et cetera, et cetera. Seriously, I'll let you guys go through this, you know, when you're studying and reading on your own time, because I would just read this all to you anyway. It'd be boring. So, but this should give you food for thought, right? All these different things. I mean, there are a lot of different ways to think about glycolysis. I think that's one of the points I'd like to make, you know, in terms of what's happening. So you should strive to like focus on the important points, and we'll turn our attention to the exergonic steps and the points of regulation shortly. Okay. Do I want to say anything here? I know I'm going to pick up on this in the, is this the last slide? Yes. I mean, I've already mentioned this a little bit, but there's a little bit more to say here. We're going to pick up on this like immediately. I'm going to open the next set of slides. So when pyruvate is anaerobically broken down, we actually regenerate NAD+. And this is actually, even though we want NADH as an energy currency of the cell, one of the energy currencies of the cell as an electron carrier, we also have to think about the need to maintain a supply of NAD plus for glycolysis, right? Because that is a substrate of glycolysis in the payoff phase. So some of that needs to go back to glycolysis. That's one consideration. If we have aerobic conditions, Pyruvate is going to be oxidized to acetyl CoA, and that in turn is going to be fed into the citric acid cycle, which we're definitely going to be talking about in some detail. So I think we've mostly covered this, but we will now pick up on this in a little more detail. Okie dokie, I have to think. Kind of want to see where we are in terms of the schedule. That now would be a good moment to think, since we don't have a lot of time left. What is today? The 7th. Oh, we're in pretty good shape, I'll say that much. So yeah, okay. I mean, I'm going to talk a little bit more today. I'm going to show you what's next, but the thing to keep in mind is the good news for you guys is I just did a few slides on chapter 13, right? So the next test is really going to just be chapters 14 and 15, but it's coming quickly. It's going to be a week from Wednesday, right? Wednesday of next week. I also want to mention that I don't know for sure, but I might do this lecture virtually. I have a situation, not to involve you too much in the trials and tribulations of my personal life, but I have a 15-year-old beagle with bladder cancer. I know, poor guy. He's already had one operation, and I'm discussing with his doctor a second operation. So I'll either proctor this exam myself or have someone else proctor it. And I might hold this lecture virtually because his vet is not here in New York. I have this outstanding vet, but he's in Virginia because I lived in Virginia for a while and he's amazing. So it's possible I might hold this, just to give you a heads up, I might hold this lecture virtually. I'm sure you can cope. And I may or may not be here for this exam, but that really doesn't matter. Someone has to just sit here and hand out the exam and collect them. So that's a heads up. Then we're going to go on and we're going to do the citric acid cycle and oxidation of fatty acids and oxidative phosphorylation. And that's going to be basically chapter 16, 17, and 19. I'm probably gonna, by Monday, I'm probably gonna be a little ahead of schedule, which is good because hopefully I'll already starting to be getting into citric acid cycle before exam 3. I think it's good to know, like just have the framework, because this is going to be a lot to cover in a short amount of time, and you're not going to have a lot of breathing room between July 20th and August 1st to like take all that in. So I hope to get to the citric acid cycle even before exam 3. Okay. Oh, wait, what am I doing? I'm already here. I'm just copying this to our website here in case you're wondering what machinations I'm involved in currently. How many courses have I taught? A lot. I have such a laundry list. Hello. Okay, so the remainder of chapter 14. If for any reason you have the newest version of the textbook, does anyone? No, we all have older versions. There's been some rearrangement. So regulation is, I'm pretty sure, part of your actual chapter 14. They moved it around in the newest edition I have. You know, the publisher sent me the newest edition. Anyway, you'll figure it out, or if you're having trouble finding the material, let me know, but it's all in the index of your textbook, right? So you can, I have great faith in your ability to figure all that out. I just don't want you to be confused by, you know, because we're going to be talking now about glycolysis, gluconeogenesis, and regulation. So we want to consider those all kind of together. Because as I say, depending on what's going on in the cell, you need one or the other, right? I'm going to come back to this first slide, and I'm going to talk about fates of pyruvate again, which we just looked at this slide. Oops, this slide. But I would like to talk a little bit about lactic acid. Oh, okay, it's a sign. We're going to pick up with this next time. The computer doesn't want to go on. Neither do we. And we only really have 9 more minutes. So.